I like to thank the viewers for selecting my video. In this particular lecture, I am going to cover on compressibility of fluids. So before going into the actual compressibility, let's understand how the solid and fluids behave with respect to compressibility. In universe, there are three states of matter. One is solid, another one is liquid, and the third one is gas. Solid, liquid, and gas. These are the three states of matter. In fluid mechanics, this we are going to study as a fluid and this as solid. So we are going to see the behavior of solid and fluid with respect to compressibility. For which for demonstrating compressibility, I am going to show a simple example. Say I am taking a solid object and I am applying a normal force that is in the perpendicular direction of the object. Because of this normal force, what happens is the object starts deforming till the elastic state. Okay. So once the force is being removed, what will happen is the object regains its original shape. This is called the elasticity of an object. Similarly, let's assume a liquid inside a beaker and I apply a normal force on this liquid substance. Here again, because of the force, the liquid starts deforming, okay? And once the normal force is being removed, it regains its original shape. So when you compare solid and liquid with respect to elasticity, it has the same behavior. Fine. Now, let's assume the same solid. Let's assume the solid is fixed at one end and I apply a shear force at the top half. Because of this applied shear force, my object starts deforming in this pattern, and once I remove the shear force, it regains its original position, that is, it regains its original shape. This happens till elastic liquid. Now, similarly, for the same liquid, I apply a shear force. Say for this particular region, for this portion of a liquid particle, I apply shear force. Now, let's assume it has displaced by this point. Once the shear force is being removed, the object does not come back to its, or the liquid particle does not come back to its original shape. So this is a major difference between a solid and a liquid. That is, when you apply shear force, it behaves differently. Fine. In order to understand compressibility and another phenomenon called bulk modulus, the relationship is given by bulk modulus K is equal to 1 by compressibility. Let's understand this particular relationship by using three examples or three different states of matter. For example, I have taken solid, liquid and gas, steel as an example for solid, water as an example for liquid, and air as an example for gas. When you compare the bulk modulus values of all these three matters, say for example steel, it is 80 gigapascal, for water it is 2 gigapascal, for air it is 0.1 megapascal. When you, based on this particular relationship, we can very much clearly say that the steel which has the highest bulk modulus is going to be the least compressibility of all three, and the water which has 2 gigapascal has less compressibility when compared to solid and water, solid and liquid, and air which has the least bulk modulus has more compressibility possibilities. Having understood the compressibility properties, let's understand the governing law called as Pascal's law. The Pascal's law it states that the pressure applied on a fluid at rest is equal in all directions. Okay, so let's understand that particular law by using a simple derivation. So here I am trying to take an element. Here I am considering an element A, B and C. A, B and C, which is of unit thickness, okay, and the direction or its displacement. This is my X, this is my Y, this is my Z, and the phase AC, which is parallel to X, is called dx, and the phase AB, which is parallel to Y, is called dy, and this particular phase is an inclined phase, which is called ds. Okay. So considering the phase AB, we have pressure Px acting in the x direction and pressure Py acting in the y direction on phase AC, and pressure Pz acting on the phase Dz. Okay. So now let's resolve the force components of all these of this particular element. For example, force acting on, let's say, on phase AC is given by Py into AC, that is Py into AC is being replaced by dx. Okay, and force acting on this phase AB is given by, the force acting on AB is given by Px into AB, which is equal to Px into dy, because AB is nothing but dy. Similarly, the force acting on BC is given by Pz into BC, that is nothing but Pz into ds. So this is my equation 1. Okay. Now I'm trying, I'm resolving the theta components of all these. For example, I'm considering the triangle AB and C, and I assume this to be theta. Okay, and so obviously this is my ds, dx and dy. So my cos theta becomes, cos theta is adjacent by hypotenuse, that is dy by ds, that is nothing but dy is equal to ds into cos theta, and my sin theta as per this term is dx by ds, which is written as dx is equal to ds into sin theta. So this becomes my second equation. Okay. So having found out the force component and the angular component, I am trying to resolve this inclined force into the equivalent horizontal and vertical component. So this becomes my Pz cos theta, and this becomes Pz sin theta. Okay, so now I write the third part. The third part, that is the forces acting in the x direction, the combination of all the forces acting in the x direction, the combination of all the forces in y direction, resolving into horizontal and vertical component. So the forces acting in x direction is px into dy minus pz into cos theta in the negative direction. Pz into cos theta into acting on the phase ds, which is equated to 0. Now I am rearranging it and say cos theta into ds. Okay. Now what I am doing is I have already derived the values for this. That is ds into cos theta is dy. So I am replacing px into dy is equal to pz into dy. I am dividing the both sides by dx and get px is equal to pz. Similarly, I am trying to write all the force component in the y direction. That is Py into dx is one force component and Pz sin theta into ds, that is acting in the negative direction, is my second component. So I am writing the equation. P y into dx minus Pz sin theta into ds is equal to 0. So I had Py into dx is equal to Pz sin theta into ds, and I have already derived the value for ds sin theta, which is ds, and replacing it here. So I get Py to dx is equal to Pz into dx. I divide both sides by dx and I get Py is equal to Pz. Now when I compare, I am comparing Py, Pz and this particular term, then I get the output as Px is equal to Py is equal to Pz. That is, the Pascal's law is being proved here. That is, it states that for a force acting on a static fluid, the pressure is equal in all the directions. That is, Px is equal to Py is equal to Pz. Having understood Pascal's law, that is, the relation is Px is equal to Py is equal to Pz. I am trying to demonstrate this particular compressibility by using a simple example called hydraulic lift. Okay. So I am assuming a hydraulic lift here. I have this piston 1, piston 2. Okay, this is area 1 and this is area A2, and I apply a normal force F1. I get an output force of F2 in the section 2. Okay, so the fluid, I assume I fill a fluid here. Okay, so as per Pascal's law, if we apply a force here, it is being uniformly distributed and we get an output force that is acting on this particular area A2, and we get F2 as a resultant force. So this is given by the relationship, that is F1 by A1 is equal to F2 by A2. Now I am more interested in the value of F2. So I am rearranging as F2 is equal to F1 into A2 by A1. Okay, so this is a relationship for the force and the area. Okay. So in order to understand it better, I am giving some numerical values to it. Say I assume I apply a force of 10 Newton for an area of 100 meter square as A1 and 200 meter square as A2. I am more interested in the resultant force or the output force that I get in F2. I am substituting the values here. That is, F1 is equal to 10 Newton into A2 is given by 200 meter square divided by A1, which is 100 meter square. So I get 20 Newton. That is, F2 is equal to 20 Newton. This is how the force is being multiplied, okay, and it is being applied in an example called hydraulic lift that works on the basic principles of Pascal's law. From F2, it is very much clear that the F2 is manipulated or it is increased because the area of section 1 and section 2 is different. Otherwise, the fluid, the force that is applied on this piston one is being transmitted by means of the fluid without any compressibility, and it starts pushing the section 2 and we get a resultant force as 20 Newton. And this is a simple example wherein we can understand compressibility of fluid very well. And I have specifically developed a particular model in order to demonstrate the compressibility of fluid, which we are going to see now. Thank you.
இது அந்த பக்கத்தில் பின்னாடி இப்போ இந்த இடம் மூவ் வருது அந்த இது நடுவில் நவுறுது நடுவில் நவுறுது அதை காட்டு இந்த கேப் எல்லாம் காட்டுறாங்க இந்த கேப்லாம் இதை தூக்கி இந்த பக்கம் பிஸ்டனை காட்டுங்க இந்த இடத்துல காட்டு வெளியே ஜூம் அவுட்